One of these days I'm going to say something very gossipy as I start the video. Start some rumor. What kind of rumor could we start? We're going to learn about tension. You're probably going to want something to jot on, some paper and pen for this one, because we're going to do some problems. Tell me what you think when you hear the word tension.
Resistance.
We're recording. Sexual tension. I didn't say it. It wasn't me. Yes. We need to do one of those. Have you guys watched The Office? You guys watch The Office? We need to do one of those like meetings where they do the, the workshops.
Oh,
Yeah. Cultural appropriateness and all that. To do with physics, what do you think of when you hear tension, Thomas? Okay, yeah. So you pull a spring and there's some tension there. Where else? Give me another situation where there's tension. Yeah, Connor.
Any kind of stress on anything.
Any kind of stress on anything. Okay, so if I take a piece of string and a roll of tape, and I tape, can they see this? Got to tilt it down a little bit. If I take this and I put it here and I pull it, where is there tension? So in the string, right? Give me an object.
Platypus.
Poor Sam. That's how I see Sam. Sam is being pulled by a rope. What is pulling Sam?
A truck.
Truck. Who's in the truck?
Me.
Who?
Santa Claus.
Oh, Santa.
Sam's dad.
Mr. Espenade, I think you need to tilt the camera up like a little bit up, just a little bit.
Thank you for
You can't
that.
get the beautiful
They need to see my Santa, right?
Santa's dream there. That'll work.
Oh, it's better. Let me turn this light on too.
See, this is a goatee.
So Santa is pulling Sam. You need some red, right? Christmas in May.
Santa's true joy.
There is tension in this string. Okay. So pick a point in this string anywhere. Let's say right here.
Oh, I was gonna say the middle of it.
The string doesn't break, and so there must be a force, right? Truck has a force going forwards, and Sam is being dragged forwards. So, in which direction is the tension in the rope? Some of you are saying this way, and some of you are saying that way, and you're both correct. There is tension this way, and there's tension that way. And this is true at every point along the rope. Where Sam is concerned, it's a little bit different for Sam, and it's a little bit different for the truck, right? So the truck has a force, we'll say a force applied forwards. Okay? And the force of tension on the truck, so get rid of the rope spot and say, as far as the truck is concerned, there's applied force forward and there's tension backwards, right? What about for Sam? What are the forces acting on Sam?
Friction of pavement.
Good, there's gotta be some friction pulling back on him, right? And what about what's pulling him forward?
The rope.
Good. So Sam's being pulled forward, but you can't say that the truck, technically the truck's not pulling Sam because the truck's not attached to Sam.
Technically,
Tension
they're
on the
right.
rope.
So technically it's the tension on the rope going this way. Okay. Now, so truck, applied force forwards, tension backwards, equal. Okay, there's probably actually some friction in here, but we won't worry about that right now. Pretend it's still there, but it's not there. Sam has friction pulling backwards, tension pulling forwards. Pretend he's not there. He's still there, but pretend he's not there. What are the forces? Just think of the rope. The truck is still here, Sam is still here, it's still being pulled. What are the forces on the rope?
Sam is a truck.
It's holding.
Well, we won't worry about gravity for a little bit.
Oh, yeah.
Well, there's like
Is there force on the rope?
Yeah.
Yes.
How do you know?
Because
There's tension on
there's
it.
tension.
If the truck pulls hard enough and Sam digs in his heels, what's going to happen to the rope?
Sam.
It's going to break, right? So there's obviously some kind of force on the rope. We call that force tension. In which direction is the tension?
Oh.
Both ways.
Good. On any rope, cable, string that's being pulled, if you're pulling something along, there's always tension in that rope. And if you look at any part of the rope, if you say, I just want to look at this half of the rope, it's the same. And if I say, well, I just want to look at this little chunk in the middle, right? Just right there. It's the same. There's tension going that way, tension going this way. In fact, that tension, this is going to weird you out, I'm sorry. If you're like if you just want the simple physics 11 stuff, stop listening right now. If you're a person who really needs to understand something deeply, then take this in. There is tension in everything. If you take a box of Kleenex and you pull it along a surface, there is tension in here. Friction's pulling back and applied force is pulling forwards, but all along in every part of this box, there's tension forward and tension backwards. Do you think if I pulled this hard enough, would this box rip apart?
Yes.
No.
Yes. The answer is yes, 100%.
Without a doubt.
Without a doubt. If I pulled at this blackboard hard enough, it's not a blackboard, it's a whiteboard, whatever. I don't see glasses. If you pull this hard enough, this would come apart.
Yeah.
Now, we don't see that very often, but it does happen. What keeps us from just ripping apart under any force? Like, think of a person. If I held my hands out and somebody pulled here and somebody pulled there, this is kind of a bad thought, but if somebody pulled hard enough, I would pull apart, right? So why do I not just fall apart like right now?
Because you.
Peria. Okay, so there's pressure pushing me in. That's part of it. How come if I pull some object, if I pull on this, I can just kind of lean on it? It doesn't come apart. Thomas.
It has tension inside itself.
Good. It has tension inside of itself. Thomas, continue.
And then maybe the mass is
So it has something to do with mass and matter, right? What is matter made of?
Stuff.
Magic. Stuff and magic.
Yeah.
That's physics 11 in a nutshell. If I chop something up into smaller and smaller pieces, what's the smallest piece? Atoms. Molecules.
Or sub.
Those atoms and molecules are held together by forces. And when you get right down to the smallest piece of matter that we have seen, there are 4 forces holding those particles together. You don't have to know about those forces or the particles or anything yet. But just know that you think of things as solid. I assure you they are not. This is mostly empty space. And so you ask, well, why doesn't it happen? I can do that 100 times. My hand will not go through the table.
Because tension.
Kai, talk to me.
It's because your atoms just keep hitting those atoms. I think it's something to do with one weak or strong force.
I can tell you with a very high level of assurance, 5 sigma result, that none of the atoms in my hand actually touch any of the atoms in the table.
Yeah, that is true.
Kai?
Is it because of the strong or weak force? 'Cause I don't know which one it is.
It's partly because of the strong and the weak force. My atoms are held together and they're held onto other atoms because of the strong force and the electroweak force. They're also held apart from other atoms because of repulsive forces. Protons and protons do not like getting put together.
They do not.
And electrons do not like being put together with other electrons. And that's what keeps my hand going through the table. Okay.
Where does gravity fit into that?
I was afraid you were going to ask me that. There's something called the Great Chasm of Physics. And it's a problem. It's what I would like some of you to spend some time thinking about and working on. You can divide up physicists into 2 categories. Physicists who work on really small things, particle physicists, and physicists who work on really big things, astrophysicists, cosmologists. Astrophysicists and cosmologists work with gravity. Gravity works really well. The theory of gravity works really well on big things. You don't have to worry about quantum mechanics when you're working on big things. The small particle girls and guys are working at a very different level, and quantum mechanics works for particles. The interesting thing is that gravity does not. Mathematically speaking, gravity and quantum mechanics cannot exist in the same universe.
Why?
You have to ask God that one. But I can tell you that they should not exist together. There are incompatibilities. But what's happened over the last 100 years is that the astrophysicists are like, yeah, gravity's good. We're good. We're going on here. And the particle physicists are like, yeah, the quantum's good. We're going. And they don't really talk to each other that much. These people work over here and those people work over there, and they do their things. But the overall physicists know this cannot continue forever.
Yeah, isn't the point to have them work?
No one ever calls me. I'm just gonna find out.
So quantum mechanics and gravity cannot work on the same thing. Is that what you said? Quantum mechanics and gravity cannot work on the same thing. Is that what you said? How is that related?
Hey Adam, you're supposed to grab something at the office. Okay. So you have astrophysicists, you have particle physicists. And by the way, you don't need to know any of this. This is not physics. Should we get back to physics 11?
No.
I mean, you could, but why would you want to?
Yeah, he's like, yes, please. It's interesting. It's interesting. Look up. You know what? I'll post it for you. I'll post it for you. Somebody remind me to post the map of physics. The map of physics. That's good. It details all this stuff. Okay. You need to learn how to do tension problems. And so I'll just kind of carry on with this. Who here skis or snowboards? Okay, you've ridden a chairlift up. As you ride up the chairlift, there's tension in that cable. And really this tension occurs in anything that's being pushed or pulled. It's easy to visualize in a nice long thin object like a cable or a rope or a string. It's really in everything, and it's an internal force that acts at all points along that thing being pushed or pulled. What happens on a chairlift is if the tension is too great? It'll break. Yeah, it'll break. So if you're an engineer and you're designing a cable, let's say for the peak-to-peak at Whistler, big thing. What kind of things do you have to take into account? The weight. So you need the weight of just of the gondola
And the people inside.
and the people inside
Like how many people can.
and how many people might be in there and equipment and all that stuff.
The temperature outside.
Good. The temperature is going to make a difference because the cable will expand or contract. There's a lot of things that you can add into the formula. The base problem is what tension does that cable need to withstand? We can test in a shop, in a machine shop, we can test how much pressure that cable will withstand. We can actually break it with really big machinery. And so then we know the point at which it breaks. Do you want to be close?
No.
Or do you want the cable to be 2-3 times stronger than it needs to be?
2-3 times.
Yes, definitely want to be bigger. Have I told you about the stadium in Brazil?
You told us about the bridge that collapsed.
I think it was Brazil. I don't want to pick on Brazil, but I think it was Brazil. And this is when I was in university. A stadium was built, and it was built to withstand the weight of all of the people who were going to go into the stadium. And early on in its lifetime, there was a game, a soccer game, and all the fans came to the stadium. And it was a local team, and they were qualifying for something. And it came down to the last minute, and there was a penalty awarded. And so the guy was ready to kick the penalty shot, right? And everyone, and he shot and he scored. And what did everyone do?
Jump out.
Everyone jumped, and the stadium collapsed. Why?
Because
It was built to the exact.
It was built to support the weight. But what happens to the normal force when you jump?
it goes up.
It increases quite a bit. So every 200-pound person in there the force became 400 newtons, maybe even 5. And so the effective weight that the stadium had to exert was doubled instantly, and it couldn't hold it, and it collapsed. And so you have to do kind of things like that too if you're looking at something like this, because you don't know what's going to happen, right? There could be a snow load, or there's things where if the gondola stops, all of a sudden you have this extra stretch, right? So you got to make it bigger. Okay. Here's the problems that you will have to solve.
No.
You have a mass and another mass, and they're going over a pulley. Right? And so I had a string of rope around here somewhere. Where did it go?
You're trying to do so.
Let me see if I can find a pulley. here I have a pulley. And, oh, I guess you will do. And if you put the string through the pulley, and you're gonna play with lots of pulleys like this. It creates an odd situation, right? A pulley. Because what happens when I pull down? Yeah, and so in this case, direction gets all befuddled, right? What's pulling the tape down?
You.
No, I'm not pulling the tape down.
Gravity.
Oh, the tape.
I'm pulling the tape up, right?
Gravity is coming.
Gravity's pulling the tape down. So even though I'm pulling down, I'm pulling against gravity. Yes?
Yes.
Yeah.
So this is weird. Creates a strange conceptual problem. And the way you solve that problem is you say, no, I'm not worrying about gravity and pulling it up and down. I don't like that. So what we're going to do, everyone put their hands like this. This is the pulley in the middle. One force on this elbow, go like this. The other force on this elbow, like this. Okay? Now go like this. Now you have a tug of war. So this elbow, this force going this way, and the other force going that way. Does that make sense?
Yeah.
Okay, so let's say you have two masses. What would the force of gravity be on M1? Negative 9.8 times?
9.8.
Times the mass, right? So this is going to be M1G pulling down, right? If you want to calculate the force, you take the mass and you times by 9.8. And that's going to be the force pulling this M1 down. Yes? Over here, what's it going to be?
M2.
Good. You know what? I like to just go like this. Let's do little m and capital M. How about that? Is that acceptable? So this is going to be little mg. This is going to be big mg. What's going to happen if this big M is bigger? And you let it go? What's going to happen?
The little one is going to go up and the big one
This one, the little one's going to go up, and the big one's going to go
down.
down. It's going to accelerate, right? But is it going to accelerate at 9.8?
No.
No. Because this one's being pulled backwards by this one, even though, and this is the weird thing about the directions, right? In which direction are these masses being pulled?
Down. M is going down.
They're both being pulled down. But this one's going to accelerate up, and this one's going to accelerate down. And we need to know what the acceleration is going to be. It's not 9.8. More than 9.8 or less? Less, because this force down is going to be working against the gravity of this one. So here's how you do it. Think about it like this. I've drawn it here, but I'm just gonna draw it bigger. Oh, this is annoying. So we have M that goes up over our pulley, and we have M. We're going to do the unfold thing. This is easier conceptually. I understand it doesn't do that in reality. But being able to unfold it is nice to think, okay, now I just have mg is being exerted this way, and big mg is being exerted that way. So this is a tug of war. Who's going to win? That's true. I always win. Big M or little m?
Big M.
Big M. We can calculate these as numbers, right? If this mass is 1, this is going to be 9.8. or 10. If this mass is 2, this is going to be 20, right? If I have 20 newtons pulling against 10 newtons, who's going to win? 20. The net force is always the sum of all forces. Yes? So, it's going to be mg plus big mg, right? But if we add them together, aren't we just going to get a bigger force? That doesn't really work, does it?
Well, they're going in opposite directions, so
Ah.
we minus them.
Very good. We have to account for direction, and this is where it's weird in your brain because you're going to think they're both being pulled down, and down is negative. But they're kind of being pulled in opposite directions,
Yep.
right? They're being pulled against each other. So even though we've done this kind of engineering trick where same direction is opposite direction, those forces are working against each other. So we have to decide
Left is negative.
which is positive and which is negative. Sam, you said left is negative. Why?
Because I don't like left sides. I'm a right-handed guy, so.
I don't appreciate your directionism. No, I would make left negative too, but for a different reason. Ashley?
The left side is going to be like a smaller number, so, and like having your answer positive is just like nice, so.
Good. I agree. I usually make the bigger side positive just because it seems to make more sense. You know, the bigger one wins, and it wins by a certain amount, and you just take this one, you minus that one, and it kind of makes sense. It doesn't matter. You can make this positive and that negative too. It's up to you. It's completely arbitrary. You'll come out to the same answer. I encourage you to do it both ways. Find the answer. Okay. In this case, F net is going to be big mg plus little mg, but we have to say that this is a different direction, right? You see how math works, right? Math is not real. Don't tell Mr. Randall, okay? We just made it up. It's just like, we saw the world and we were like, well, I think this fits. Let's try that, okay? I'll show you why math is artificial in a little bit, but not right now. So we have to say, oh, but this is negative, right? And so up here, we would really say, I'm just going to erase this part here. Keep in mind that's positive. And so we make this negative. And when we add them together, it kind of becomes a minus, right? Now, you have to decide with these types of problems. I'm going to have you make a decision right now about yourself. Get in touch with your brain. Are you feeling your brain?
No.
Try to feel your brain.
No.
Not like this, but, well, maybe. That might help too. Oh, I have tinfoil hats too. Anybody want a tinfoil hat?
Yes.
Who said yes?
Yes.
Kai, come on up. Thomas, you want to?
Yes.
It'll help you get in touch with your brain. Oh. Whether you're wearing a tinfoil hat or you're just touching or you're thinking,
This is 60. Oh, yeah.
you have a decision to make. You're either a real world type thinker or a mathematical type thinker. And you'll solve problems in different ways depending on your tendency. Now, I'll say right from the beginning that as you go on in physics, you will need to do both. And eventually you'll interchange really easily. But I always think in the beginning it's nice to know which way you are, and you can pick one way and you can do it that way. If you are a mathematical thinker, you will just say F net is F1 plus F2. And F2 just happens to be negative. You just add them up. And every time you add them up, but you have to be aware of your negatives and positives.
Yes.
If you're a real world thinker, you're gonna say, no, I don't need any of that. I know that the bigger one wins. And so it's just big minus small. And that's how much the big wins by. And that's good enough. Okay. Either way is fine. There's no wrong way to do this. Okay.
Wait, if you were to write that like mathematically, would you do like x and then the arrow thing and then x with the opposite arrow thing? If you know what arrow thing I'm talking about?
You mean like a vector arrow?
No, like you know how in
Oh.
elementary they do like the bird feed thing, where it's like one number's bigger than the other. It's like that.
Oh, yeah.
Yeah, would you use that for like the big minus small?
You could, I guess. Oh man, I think I'm wrecking my board. Do you want to do an example?
Sure.
Give me a number.
69.
It's too big. Single digit number.
4.6.
2. Another number?
4.
6.2.
4.
4.
Oh.
Find the acceleration. Go.
2.
No, wrong.
Should we know?
Should we do it together? First thing you do is this. Right? You have 2, and you have 4. Can we agree that for these examples, we'll just make g equal to 10?
Yeah.
10 meters per second?
Yeah.
I'm not going to put negative because there's no down and up here, right? What's the force on the 2? 20 newtons pushing down, and on the 4?
40.
40 newtons. Just 2 times 10, 4 times 10. Right? When you stretch that out, you have 20 newtons going to the left and 40 newtons going to the right. Yes. Who's going to win, Peria? The 40's going to win. Okay. So we say, if you're mathematical, you're going to say, wait, there's something else we have to do. What else do we have to do?
Figure out which one's negative.
Which one would you make negative?
The 20.
I'd probably make the 20 negative, right? F net equals 40 plus negative 20, which equals 20 newtons. If you're mathematical, you're going to do it this way. If you're real worldy, you're going to say, nope, I don't care about this negative. Bigger beats smaller, 40 minus 20 equals 20. And if you're a real worlder, you're going to think it's 20 to the right. Okay? Which is really down for this guy. Right? Either way, F net equals 20. What's the formula for F net? MA. Now, which M do we use? The whole object. Forget there's a rope and 2 masses. Imagine this is one big mass, and you're pulling it 40 to the right and 20 to the left. What would the mass of that object be? 60. 60. You have to use the total mass, right? Because we want the total acceleration. Yes? So we're going to say F net over M equals A. So what's our F net? 20. Over? 60. So this is going to be 0.3, right? Meters per second.
Wait, but isn't the mass in grams? Isn't that only 2 and 4?
Oh yeah, sorry, that's not right. It's not 60. What's our mass? 6. Yeah. I thought that was really small. Yeah, don't get confused with that. Newtons are force, right? So 20 newtons, 40 newtons. But these would be kilograms. So we would have to do 6. 20 over 6 is 3.3. Is that right? And that would be our acceleration. Does that make sense to you? Sounds about right. This would accelerate at 10 if it were left alone. But it's being pulled back with a weight, 50% of it. And so it cuts it down to 3. The next question I will ask you, which you don't want to hear. Oh, should I give you another one of these first?
Yeah.
Okay, let's do this. Do this one. I'll leave this example up here. Find the acceleration of this system. You should be able to do it in your head. You don't have to write it down.
1.6. 1.7.
Oh, yeah, maybe.
1.7.
1.7 or 1.5?
1.7.
Isn't it 1.5? Oh no, yeah, you're right, you're right. Yeah, 1.7. Thanks, Ethan.
Oh, okay. Yep. Yeah. 1.7.
Right. .6 repeating. Yes. Okay, how did Ethan do that so fast? Matthew, tell me.
70 minus 50. And
You're a real world thinker, yeah?
yeah.
Okay.
And then you just divide that by the total.
Good. So Matthew's saying if we have 5 and 7, this is going to be 50 and this is going to be 70, right? Isn't it nice when you make G equal 10? Sorry.
Yeah, but like.
So your net force is 20 to the right, right? Can you all see that?
Yep.
Whether you do it mathematically or real world, you're going to come out to 20. And so F net divided by the mass is the acceleration, right? But which mass do we use?
The 5 plus 7,
We use the total mass, right?
which is 12.
So your 20 newtons divided by the mass of the whole thing,
Which is 12.
because that's what we want to find the acceleration of, right? Is the whole thing, not just one mass or the other. We want to find the whole thing. So you go over 12, and that's going to be
1.6.
12.6 repeating. That's
1.6 repeating, which
is
Ethan rounded to 1.7.
Yeah.
And that's your acceleration. Yeah, Thomas.
Would the F net be the absolute value of F1 plus F2?
Say that again.
Because would it be the absolute value of F1 plus F2? Because if it's 50 minus 70, you get negative 20.
Yeah, that's correct. But negative 20 is fine because then you're going to get a negative acceleration, and negative in that case still means to the right. So that's fine. Matt, Thomas is asking a good question. He's saying, if you say this is negative and this is plus, can you still do that? Well then, what's this answer going to be?
Negative 20.
Negative. And then this is negative. But the 12 stays positive, right? Mass is a scalar, so there's no negative there, and so this would be negative. So how can I have positive 1.6 and negative 1.6? How can those both be right?
Change the top.
Ashley?
Because it's all about direction.
Right, and
The
so,
negative isn't saying like, oh, it's negative, it's saying that it's 1.6 repeating to the right. You just happen to make right negative in this case.
yeah, exactly. So because the positive and negative is arbitrary, we just have to know that this one is going to drop, this one's gonna rise, which in our symbolic opening up is right and left. So it just has to come out the right way. Whether you call it positive or negative doesn't matter. Try to make this erase properly. Okay. You're doing very well. This is the crux of it right here. So we've opened up the system here. I'm gonna see if I can clean this. How's my phone doing? Is it still working?
Yeah.
Okay, so we already kind of did this, so we'll skip to the next one. I think the glue from the whiteboard eraser got in there. Anyway. Okay. Let's try this. You have 6 kilos and you have 4 kilos. First, find the acceleration of the system, and then try to find the tension force in the string. So find the acceleration first.
2 meters.
2?
Yeah.
You think it's 2? The net force is 2. No, the net force is 20, right? Oh yeah, you guys are quick. If you didn't get that right away, work that out in your head. Now see if you can find the tension force. How would you do that? Any ideas? Put your hand up if you got it. Put your hand up if you don't know what to do. I don't know what to do. Okay, I'm going to show you. It's good that you've thought about it for a bit. Let's find the acceleration first. So we have 6 and 4, yeah? And if we spread that out, I'm going to draw it a little bit shorter. What's the net force on the 4? 40. So this is being pushed 40 newtons this way. And here? And so my net force is 20 to the right, right? And what's my acceleration?
Zero.
20 newtons over
10.
10 kilos, because that's the whole deal, and we have 2 meters per second squared. That number is the key to finding the tension force. Here's what you have to remember. These 2 blocks are tied together. So their acceleration must be equal. Yes? This is not going to drop faster than this one unless the string breaks, which we're going to assume the string does not break. So, for a moment, pretend this doesn't exist. Is this being pulled only with 60 newtons?
No.
No. There's another force pulling backwards on it, right? What is that force?
-40.
Is it -40?
Oh, actually, there's no other block, right? You got rid of the other block.
Well, there is another block over here, and it's being pulled with -40, but is that the same force that is pulling this?
No.
Yeah. If they're tied together, then yeah.
They're tied together, but it's not the same force. I'll tell you why. Because this is accelerating at 2 meters per second squared, right? But it only weighs 6 kilos, right? So now what you have to do is you have to say, let's find the net force, but not the net force on the whole system. Just the net force on this block. It's different. Does that make sense? If you look over here, you go, this is being pulled down by gravity, but it's also being pulled up by tension. The tension's being created by this block, but it's not the same as the force here. Okay, so I'm going to say F net 6. This is the net force, but just on this block, not on the whole system. How would we find that net force?
Times acceleration.
Good, easy. Mass times acceleration. We know the acceleration of the block, right? Because the whole system accelerates, and each individual block accelerates at the same acceleration. They're tied together, so they have to. Their motion has to be the same. But the forces do not have to be the same. Okay? So, what's my mass? 6. In this case, we're just finding the net force for this block. So we don't want to use the whole mass. We want to use just the 6. And what's my acceleration? 2. We calculated 2. We're going to make it positive 2, because this way was positive anyways. So, what's my net force? 12. If you're mathematical, you're going to say, well, F net equals, let's say, this is FG, and this is FT. We don't know what it is yet. So you're going to say, this is FG plus FT. This is the mathy way to do it. Okay. We'll, mathy, ding. If you're mathy, you're going to say, the net force is always the sum of forces. Always. We want to find this one. So how do we solve for it?
You just plug 12 in for F net.
Wait, hold on. Don't plug in anything yet. How do we solve for FT?
Oh, F net divide.
How do we get rid of this?
Divide on both sides.
I don't know.
Oh, no, mine, bring it over, sorry, mine.
Good. We're being added. We're adding, so we're going to subtract it over. Very good. Equals FT. So, what was my net force for 6?
12? Oh, 12.
12.
12 minus 16.
Minus FG, which was 60. So what's my FT?
Negative 48.
Good. Negative 48 newtons. if you're real worldy, you're gonna say, look, 60 wins, because the thing is moving that way, right? It's accelerating to the right. And it has to win by 12, right? So you just go, if you're real worldy, you just go ft equals fg minus minus the net, right? No, net minus fg. How would you do that? Give me a real worldy thinker. How would you do it? You would say this is gonna win,
Oh, FG.
and it has to win by 12. So this minus 12 has to equal this, right? So you're gonna say, I don't know, I'll just do it numbers wise. You're just gonna say 60 minus 12 equals 48. And that's gonna be negative because it's the loser. So you're gonna say negative 48. And this is the real worldy way. Same, man. What does the negative mean? Or maybe you would just say
That's positive.
positive, but it's left. Because you know that the tension's pulling back to the left, right?
Wait, that equation does give you a positive.
Say that again.
That equation gives you a positive.
This
The
one?
other one? No, the one on the
Real
right.
world one.
This gives you a positive, yeah, but that's okay because you know it's going to the left. If you're a real world thinker, you're looking at the situation, you're going, this is going to win. So the tension is to the left, and this has to win by 12. So this minus 12 is 48. So this has to be 48, and it's going to be pulling left. But if you're a real worldy thinker, you have to keep the directions and everything in mind. Okay. Now, Peria, yes. Shh, quiet, please. Say again. Why do you use 6? I'm glad you asked. There's no reason why you would use one mass or the other. And what you can do, the great thing about tension problems is that you can always check your answer to see if you're right. Because, here's a little fact. The tension in a rope is always the same on either end. You know that because if it wasn't, one end of the rope would move differently than the other end of the rope, right? And they're not. So the tension on each side has to be equal. So let's test it with the 4. The net force of the 4 kilogram block, how would we find that? Mass times acceleration, thank you, Asia. What's the mass of the 4? 4. And what's its acceleration? 2. It's the same as everything else. Everything's accelerating at 2, right? So what's 4 times 2? 8 newtons, right? The net force of this is going to be 8. So if you look at this 4 Newton block, it's being pulled by tension, right? And it's being held back by what? What's pulling this way? Yeah, gravity. Yeah.
40.
And what's the force of that? 40. So 40 newtons this way. And my tension should be negative 48, right? So does that equal 8? I think it does. Is that right? Oh, wait a minute, this is negative. And this is also negative, if you're mathy, right? Should I explain? I gotta explain that, don't I? Here. Our net force we got was, sorry, our tension force we got was what? Negative 48. So that's what we're checking. that our FT is negative 48. And that means to the, well, no, sorry. This is going to be positive 8, right? Because it's being pulled that way.
But wouldn't acceleration be negative if we, because
This being 40,
that would be negative.
no, this is negative 40.
Negative
Because this is left, right? So our tension force here would be, do you want me to do it mathy or real world?
real world.
Okay, real world, this has to win by 8, right? So what does this number have to be?
48.
It has to be 48, right? So that has to equal 48. If you're worldy, if you're thinking real worldy, you just know this has got to win by 8. And this is being pulled to the left 40, so this has to be positive 48. If you're mathy, you're going to say, no. It's always the sum of all forces. So if I'm solving for this, I go F net minus Fg equals Ft. My F net we know is 8, right? 8 minus my Fg, which is negative 40. That's going to equal positive 48 newtons. Now you say, well, wait, hold on. The last one was negative 48.
Well, that's because it was pulling that direction.
So you have the 6 and you have the 4. The tension on the 6 is pulling this way, right? The tension on the 4 is pulling which way? This way. So it's the same but opposite direction. And that's okay. So you can always check with the other mass, and they should be equal. If they're not equal, you did something wrong. You messed up a negative sign or something. And they should be in opposite directions. You have your in-class lab, the Hooke's Law one, and I'm going to post some tension problems. I'm not seeing you guys until oh yeah, your morning class.
Yeah.
You're so lucky, you see me every day. Try the tension worksheet. I'll give you some time to work on it tomorrow, and if you have any questions, bring them to me.
When do we have to submit our lab?
Well, tomorrow midnight.